Hey everyone, let's see, last time we introduced parametric curves, and I want to continue our study of parametric curves, and we're going to start doing calculus with parametrized curves now, or parametric curves. So suppose that we have a curve, and I'm going to write it like this. This is typically how I'll write my parametric curves. If I want to give it a name C, I'll write C colon, and then x equals f of t, y equals g of t. If I want to put a certain range, I'll put the range of the t variable right over here. So let's say, suppose we have a curve where, so C is a parametric curve where both of these functions, f and g, are differentiable. So where f of t and g of t are differentiable. Right? So f prime of t exists, y prime, or and g prime of t exists. So remember, we've got some curve now. And one thing that we like to do in calculus is take derivatives, right? And if it corresponds to a curve, when you take the derivative, right, that's supposed to give you the slope of the tangent line. So what we would like to do, if we have some curve C, right, we would like to be able to find the slope of the tangent line. But now, right, when we have this, we don't have it written as a function y equals f of x, right? We can't express it as the graph of a function. But we still may want to take the derivative. And so here's how it goes, right? So we can say then, let's see, the derivative with respect to t, let me write it like this. So then dy dt is equal to dy dx times dx dt. This is just the chain rule. And my goal, I want to find dy dx. I would like to know the derivative so that I can say what the slope of the tangent line is at a particular point. And now notice what I can do is solve. So dy dx is equal to dy dt divided by dx dt. So what this does is it gives us a formula for the derivative, which will then tell us the slope of the tangent line, right? dy dx is the slope of the tangent line anytime we have a curve. We could also do the same thing. So we'll say also, all right, so here's the first derivative. You can compute the second derivative, basically doing the same thing. So the derivative of the derivative, that's equal to, so using the chain rule, that's going to be the second derivative of y with respect to x times dx dt. Once again, just using the chain rule. And so the second derivative is equal to the derivative with respect to t of dy dx divided by dx dt. The second derivative doesn't come up a whole lot. When we're dealing with parametric curves, we're really not going to worry too much about second derivative. Remember, it'll tell you something about concavity. That's not going to take I think you have a couple of homework problems that ask you to compute the second derivative, but overall it does not play a big role in this subject. So let's try an example now. So let's find, oh, and let me fill in my picture here. So this is, right, the slope, let's say this. So slope is dy dx, and it's occurring at that point right there. So that point is going to be f of t, comma, g of t. All right, so in this first example here, so let's find the equation of the tangent line to the curve So to the curve C given by x equals t squared plus t plus 1. Y equals sine of t plus t. At, so I'm going to give you the t value, t equals 0. Okay, so I'll leave my formula up here, just the first derivative formula right here. So I want to compute dy dx, and so what does that say? Create a fraction where I put dy dt in the top, dx dt in the bottom. So dy dx is going to be derivative of the y function, so that's going to be a cosine of t plus 1 divided by the derivative of the x function, so that's going to be a 2t plus 1. Now, we want the derivative when t equals 0, and so, so this is the notation, dy dx at t equals 0, that means plug t equals 0 into the formula. So if I plug t equals 0 up here, that's going to give me a 2, and in the denominator it's going to give me a 1. All right, so we get a slope of 2. Now, this line, so there's the slope. We need to know which point it passes through. So I need to take t equals 0 and plug it into the original to figure out the x and y coordinates of the point that this line is passing through. So passes through. So I'm going to take 0, plug it into each of these, and it's going to be 1, 0. All right. So we want then the tangent line has the equation slope 2 passing through 1, 0. So if you use the formula y is equal to 2 times x minus 1, which we can write in slope-intercept form as y equals 2x minus 2. Let me leave this formula up just for a second. But my words are going to follow this example. So that's the end of the example. And now I just want to make an observation. So note that a curve given by the parametric equations x equals f of t, y equals g of t will have horizontal tangents when, well, let's see, what you need for horizontal tangent, you need the derivative to equal 0, which means that we would want the numerator to be 0 while the denominator is non-zero. We don't want an indeterminate form. If we get an indeterminate form, we'd have to analyze it further. But we're guaranteed to get horizontal tangents when dy dt equals 0. I'll just put in parentheses here, and dx dt not equal to 0. And so it'll have horizontal tangents at that point and vertical tangents when, so let's see, a vertical tangent corresponds to an undefined slope, which would be non-zero here and 0 here. So when dx dt equals 0, and I'll just say in parentheses, dy dt not equal to 0. Now, if both top and bottom are equal to 0, then you need to take a limit, right? You'll have an indeterminate form, take a limit to see what happens, and oftentimes with L'Hopital's rule, you can identify vertical tangents even in the case that you have 0 over 0 initially. Okay, so let's try an example here for the cycloid. So this is an example for the cycloid. So this is going to be x equals 2. So this is going to be the radius 2 cycloid t minus sine t. and y equals 2 times 1 minus cosine t. All right, so remember the cycloid, that's what you get when you roll a wheel. Let's do this where t is greater than or equal to 0. So in this case, we're going to take a wheel of radius 2, roll it, and what I want to do, I like to find where it has horizontal tangents and where it has vertical tangents. So part A, for the cycloid, where does it have horizontal tangents? And then part B, where does it have vertical tangents? Now, let me just draw the picture real quick. There's one thing that we want to be clear on here. So here I am with a circle. In this case, it's radius 2. Take the point P down at the bottom here and think of this. So let's put P at t equals 0. Now, how far does it need to revolve for P to do one rotation, right, and end up back down here? Well, that's going to be exactly this distance right here. The distance along this axis, the x-axis, is going to correspond, right, to exactly the circumference of the circle. Right? So this distance right here, you don't even need to write this down. The distance is going to be 4 pi. Okay? But that's distance along the x-axis. So every time you do a revolution, right, you'll have traveled 4 pi along the x-axis. That is not the same as the t value. So my question, before we get going here, my question is, what is the t value corresponding to that spot right there? Well, let's see. That's going to correspond to when y equals 0, right? When the height is equal to 0. So if you set this equal to 0, that would mean that we need cosine equal to 1. That happens, well, the first time it happens is when t equals 4 pi, right? So this is, 2 pi. That's 4 pi along the x-axis, but corresponding to t equals 2 pi. The next time, right, on the x-axis, that's 8 pi, but it corresponds to t equals 4 pi. So it hits the x-axis whenever t is an even multiple of pi, right? 2 pi, 4 pi, 6 pi, and so on. All right, so we'll need that fact. In fact, let me just leave this up, and I'm going to do part A down here. And in fact, before I even do part A, let's take the derivative, right? So dy dx, so that's going to be a 2 times sine t divided by, okay, the derivative in the new of the x function is going to be a 2 times 1 minus cosine t. So if we simplify, that's going to be a sine t divided by 1 minus cosine t. So for part A, it's going to be, we're going to get horizontal tangents at any time that the numerator is equal to 0, assuming that the denominator is not equal to 0. So dy dx equals 0 when sine of t is equal to 0, and cosine of t not equal to 1. I don't want to make the denominator 0. So this occurs. Well, let me think here. The sine is equal to 0 at all multiples of pi, right? But the cosine is equal to 1 at the even multiples of pi. So what we want to do is look at the odd multiples of pi. So this occurs when t is an odd multiple of pi. So that would be, let's say, pi, 3 pi, 5 pi, and so on. Right? So we get horizontal tangents then. Let me draw the cycloid now. Right? The first one is at pi. Right? Remember, this corresponds to t. I should mark this as t equals pi. Right? So there's our first horizontal tangent. The next one would be at t equals 3 pi, 5 pi, and so on. Part B. Okay, so now for vertical tangents, what we want, right, we're guaranteed to have a vertical tangent if we can make the denominator 0 with the numerator non-zero. Unfortunately, right, I mean, when is cosine of t equal to 1, right? When can we make this equal to 0? Well, it's going to happen at even multiples of pi, but sine t is equal to 0 at that spot. So what we do then is I look at the limit as t approaches. Let's do this first one, 2 pi. Limit as t approaches 2 pi, let's say from the positive of sine of t divided by 1 minus cosine t. Now, this is an indeterminate form, 0 over 0. And so this will be limit as t approaches 2 pi from the positive side of cosine of t over sine t. Now, what's happening? The denominator is approaching 0 while the numerator is approaching 1, and so this gives us a limit of infinity. So what is that saying? So I approached, as t approaches 2 pi from the positive side, what we're seeing is that the slopes of our tangent lines are getting steeper and steeper, and then right at t equals 2 pi, right, we have a vertical tangent. And in fact, this is going to happen at all of these spots here, right, everywhere we have a bump. So it happens at even multiples of pi. So vertical tangents at t equals 0, 2 pi, 4 pi, and so on. Okay, so there's some information about derivatives. Now let's talk about area and parametric curves. So suppose the curve, so we've got a c x equals f of t, y equals g of t. So suppose this curve is traversed exactly one time, so exactly once, as t. Oh, sorry, I need to have bounds here. All right, so in this case, I want to consider over the interval from a to b. So as t goes from a to b. So our picture is going to look like this. Now, I want to have, so this is going to be f of a, comma, g of a. And this is going to be f of b, comma, g of b, right? So we've got a starting point and an ending point. And when I say traversed exactly once as t goes from a to b, what I want, imagine that this is the path of a particle, and it travels like this. Instead of, or here's something that could be bad, if it goes forward for a little while, then backwards, and then forwards, if it ever crosses over itself or over its path once, we don't want that, right? So what we want, right, you're not allowed to go forward and then backwards in any way, right? Once you've gone forward, you can't go backwards. And this will happen, so this will occur when For example, if you know that the derivative dx dt is positive, then you're guaranteed that this will happen. Now, let me clean up this picture a little bit. And I want to just take a sort of a smaller portion. All right, so let's say that we have some parametric curve like that. Starting point and ending point again. So that's a f of a, comma g of a. That's a f of b, comma g of b. And what I'd like to know is what's the area under that curve. So the area under C is, well, let's see, how do you compute area? You compute an integral. And I should be a little bit careful here. That's fine. No, in fact, the area under C, let me be careful here. The area under C over, I want to be specific about the interval here. So this point on the x-axis is f of a. This point on the y-axis is f of b. So area under C over the interval from f of a to f of b is, okay, so what are you going to do? You're going to integrate. Well, okay, let me say it. Maybe take it slowly. F of a to f of b. And then what do? You do y dx. Right? But in this case now, when we switch to the variable t, I'm going to make a substitution. So this will be the integral from a to b. And then y is g of t. And dx is going to be f prime of t dt. Right? So that integral right there will compute the area under the curve as we go from f of a to f of b. So let's try an example. Let's find the area under one arch of the cycloid. And let's just do that same one, the one that had radius 2, right? So that's going to be x equals 2 times t minus cosine t. Minus sine t. And y equals 2 times 1 minus cosine t. So if I take one arch, for example, we could do the one that goes from 0 until t equals 2 pi. So this is t equals 0, and this is t equals 2 pi. Right? Along the x-axis, this actual distance right here is 4 pi. Right? It's the circumference of the circle. But we want to integrate with respect to t, so I need to know the t value that gets us from here to here. Okay, and then I just throw it into this formula, right? So it's going to be g of t times f prime, or it's the y function times the derivative of the x function. And so this is going to be equal to, so the area is equal to integral from 0 to 2 pi. 2 times 1 minus cosine t times 2 times 1 minus cosine t dt. I'm going to pull the 4 out, right? That's a 2 times 2. And then I need to multiply this stuff out here, so this will be a 1 minus 2 cosine t plus cosine squared t dt. And we might as well just carry this out just to remind you how to integrate this stuff. So let's see, before I can integrate a cosine squared, I need to replace it, right? I need to apply an identity here. So this is going to be plus 1/2 times 1 plus cosine 2t dt. So hopefully everybody remembers how to integrate cosine squared. And then this is going to be 4 integral 0 to 2 pi. I have a 1/2 here combined with a 1, so that'll give me a 3/2 minus 2 cosine t plus 1/2 cosine 2t dt. And now we're ready to integrate. So that's going to be 4 times 3t over 2 minus 2 sine t plus 1/4 sine of 2t. And we're going from 0 to 2 pi. When I plug 2 pi into the sine function in either of these, I just get 0. And so what we'll be left with is 412, so that's going to be 12 times 2 pi over 2. So that looks like 12 pi. Right? So that gives us the area under one arch of that cycloid. A couple more things that we might want to do with parametric curves. So the next one is arc length. All right, so if you have some parametric curve, you might want to compute how long it is. So arc length and parametric curves. So the same setup as we had with the area, we can compute the arc length, assuming that as you travel along the curve, you don't backtrack, right? So you travel exactly one time. So I'm going to say that again. If we have a parametric curve, so C, x equals f of t, y equals g of t, along, and I need bounds here, a less than or equal to t, less than or equal to b, is traversed once as t goes from a to b. Once again, if you want to actually verify it, one way to verify that, if you can show that the derivative is always positive, then you know that that happens. So then the length of C is, so let me use the correct symbol. It's a little s is usually used for arc length. So let's use little s, and it's going to be the integral from a to b square root f prime of t squared plus g prime of t squared dt. So this generalizes the arc length formula that you learned back in Calc 2. Right, and it opens it up so now that we can compute the length of parametric curves, not just the graphs of functions. Yeah, you know what? Let me give you one more formula. So this is arc length. I also want to do surface area, and then we'll do an example that involves both of these. So surface area and parametric curves. So here's the idea. Let's say that you have some parametric curve satisfying the same stuff here. And you take that curve and revolve it about the x-axis. What that's going to do, it's going to generate, right, some surface like this, and then we can compute the arc length, the surface area of this. So if this same curve, so if C is revolved about the x-axis, then the area of the surface is, typically you use a capital S for surface area instead of lowercase s, so there's a capital S, and it's going to be 2 pi integral from a to b, and then it will be the, let me make sure I get this right, yeah, y. So g of t times square root f prime of t squared plus g prime of t squared dt. And then one last thing, so we can revolve it around the x-axis, we can also revolve curves about the y-axis, and so let's just give you the formula. It's going to look almost the same, except instead of a g of t here, I'm going to have an f of t. So if C is revolved about the y-axis, then the surface area, right, of the resulting surface, 2 pi integral from a to b f of t times, square root f prime t squared plus g prime of t squared dt. Okay, so there's 3 new formulas, right? We've got an arc length and we've got surface area. And so let's just do an example. And I just want to take the cycloid and I'll do a couple of things. Let's find the length of the cycloid, and then let's find the surface area, or at least set it up. I think that one's a hard one to actually compute, but we'll set it up. So for the cycloid, same one that we were doing before, so the radius 2 1. So for the cycloid, x equals 2 times t minus sine t, y equals 2, 1 minus cosine t. Part A, find the length of one arch. And then part B, set up an integral that computes the area, or the surface area, if revolved about the x-axis. And I really should say if one arch is revolved. Revolved about the x-axis. Okay, so let's do part A. So I need to take some derivatives, so let's get that dx dt equals, it'll be 2 times 1 minus cosine t, and dy dt is going to be 2 sine t. So now let's throw this into the arc length formula, integral. So it'll be integral from 0 to 2 pi. Remember, that's the t values that have it complete the first arch, right, from 0 to 2 pi. Okay, so now under the square root, here's my derivatives. I'm going to square each one of those. So this will be a 4 times 1 minus cosine t quantity squared plus 4 sine squared t dt. All right, so hopefully everybody knows where this setup came from. Now I need to multiply things out. And it looks a bit ugly. Remember, what I was saying is these problems, when they involve square roots, they can be difficult. So they have to be rigged to actually work out. And this one, it turns out, is I guess you could say rigged. So this is going to be a 4 times 1 minus 2 cosine t plus cosine squared t plus 4 sine squared t dt. And let's multiply it out another step, see what happens here. So this is going to be a 4 minus 8 cosine t plus 4 cosine squared t plus 4 sine squared t dt. And now notice right here, applying a trig identity, this is equal to 4. And so what we get is integral from 0 to 2 pi square root of 8 minus 8 cosine t dt, which may look ugly, but it turns out that we're going to be able to write this as a perfect square. What I want to do is, oh, and I think, is it minus? Yeah, it is minus. Yeah. Let me get the 8 out of the way. If I take an 8 out of a square root, right, the square root of 8 is 2 root 2. So it's 2 root 2, integral 0 to 2 pi. And then we have square root of 1 minus cosine t dt. Now we're going to need a trig identity to integrate this. So let me just off to the side here remind you of something. What we know is that 1 minus, well, let's say it this way, sine squared of t is equal to 1 minus cosine 2t divided by 2. Which means that sine squared of t over 2 is equal to 1 minus cosine t divided by 2. Right? All I did was substitute t over 2 in place of t. And now, if I solve, what we get is that 1 minus cosine of t is equal to 2 times sine of t over 2. Oh, sorry, sine squared t over 2. In other words, what we have right here is a perfect square. This is 2 root 2, integral 0 to 2 pi. Under the square root, we now have a 2 sine squared t over 2 dt. Right? This is now something that we can integrate when we take the square root. We're going to get a square root of 2 to bring over here. That's going to give us 4 out in front of the integral. So we'll get 4 integral 0 to 2 pi. And then what we'll have is sine of t over 2 dt. Now we can take the antiderivative. So this is 4 times minus cosine, minus cosine t over 2 divided by 1/2, and then we go from 0 to 2 pi. So that's equal to negative 8 cosine of t over 2, go from 0 to 2 pi. Let's see, when I plug in a 2 pi here, I'm going to get a cosine of pi, which is negative 1. So this will give us a positive 8. When I plug in 0, so that's going to be minus a negative, so plus. And then it's going to be cosine of 0, so it'll be plus 8. Okay. So in the end, the length of one arch of that cycloid is 16. And then we're supposed to set up, you could actually integrate it, but let's just set it up, right, doing the same, it would involve the same trig identity to do it. So the surface area is going to be 2 pi, integral from a to b, and then the y function is 2 times 1 minus cosine t, and then under the square root we would have the derivative squared, so that would be a 4 times 1 1 minus cosine t quantity squared plus 4 sine squared t dt. by applying a trig identity to this thing right here, the same one that we did before, you'd get something that it'd be kind of a pain to integrate, but it's actually is doable. So I guess that's a good place to stop for today, right? And so we'll see you next time.